Hi there, this is Yan. This week's topic is hypothesis testing. We'll start by reviewing a Z transformation problem. So last week we learned about a Z transformation, which is also called a standard normal transformation. If we already know the population mean and variance, and we want to find out how likely to select a particular sample mean from this population, we use Z transformation. We calculate the Z-score and then locate the proportion for the Z-score in the unit normal table in Appendix B. So this is an example in our textbook, but I modified it a little bit. The general population's IQ score, the mean is 100 and standard deviation is 15. If we select a sample of 100 graduate students, and we get the sample mean 103. So what is the probability of obtaining a score larger than 103? So first we transform this sample mean 103 into its Z-score, and that's 2. And then we find 2 in column A in the unit normal table, and then its column C is 0.0228. So we know in the standard normal distribution, this mean is 0, and the Z-score is 2, and the area in the tail is 0.0228. There are 4 steps in hypothesis testing, and I'll use the same example to explain them step by step. Hypothesis is a statement about the value for a population parameter that can be tested. A null hypothesis, or H0, states the value of the population parameter that's assumed to be true, but we think it is wrong. So as researchers, the burden is on us to prove it is not true. The alternative hypothesis, H1, or HA, contradicts the null hypothesis by stating that the population parameter is smaller or larger or not equal to the value in the null hypothesis. If the hypothesis regarding the population parameter were true, how likely would a sample statistic to be selected? And that's hypothesis testing. If it's likely, we accept the null hypothesis. If it's unlikely, we reject the null hypothesis. So let's use the same example from previous slide. We know the general population means 100, the standard deviation is 15. If we consider all the graduate students as one single population, is the graduate population's mean 100 as well? Therefore, our null hypothesis is that the graduate population is the same as the general population. Its mean is 100. So if it were true, the probability to get a sample mean of 103 would be high. If it were not true, the probability would be very small. There are 3 possible alternative hypotheses. The mean is larger than 100 or smaller than 100, and that will be a directional test. Or the mean is not equal to 100, and that's non-directional test. And that's what we're going to do in this example. Step 2 is to set the level of significance, or alpha level, for decision. It is a criterion based on the likelihood of obtaining a sample statistic if the population parameter were true. So first we assume graduation population mean is 100 and randomly select 100 graduate students and their mean is 103. If the chance of obtaining 103 is less than 5%, we reject the null hypothesis. For the mean to be different from 100, there are 2 possibilities. It's larger than 100 or it's smaller than 100. So we split the 5% into 2 tails. And these areas are called rejection regions. So each area is 2.5% or 0.025. And we called it a rejection region because if 103 falls in this area, we reject the null hypothesis. So when you go to the Appendix B on page 479 and find a 0.025 in column C, you find that the z-score is 1.96. So we know our cutoff value is 1.96 and negative 1.96. But we know 103 is larger than 100, so it can only be in this area. So in step 2, we set the alpha level at 5% and find the critical value or cutoff value 1.96. In step 2, we compute the obtained value of a z-statistic. The obtained value is the value of a test statistic, which is used to compare to the critical value of a hypothesis test to make a decision. And from slide 1, we already know that for a score of 103, after we transform it, its z-score is 2, and 2 is our obtained value. And the proportion of the area in this tail is 0.0228. So this is our obtained value, and this is the proportion of this small tail area. And in step 2, we know that the critical value or the cutoff value is 1.96, and the rejection region is 0.025, and which is the critical value is smaller than the obtained value. So this area for the obtained value is smaller than the rejection region. So now the last step is to make our decision. Since the obtained value of 2 falls in this pink rejection region, we reject the null hypothesis and come to the conclusion that graduate mean is not equal to 100. What we just did is also called a one-sample z-test. It is a statistical procedure used to test the hypothesis concerning the mean in a single population with a known variance. We just did a non-directional test, so this is an example of a directional test. The population is elementary school students, and their reading proficiency mean is 12, and the standard deviation of the population is 4. If we select 12 children from a reading program, and their reading proficiency mean is 14, and we set the alpha level or level of significance at 0.05 or 5%. And the question is, was the reading program effective? So if the reading program was effective, the mean should be higher than the population mean. So that's our alternative hypothesis. The mean is larger than 12. And to contradict this hypothesis, the null hypothesis should be the mean is equal to or smaller than 12. And the second step is to set the cutoff value. Our alpha level is 0.05, and that's our rejection region. And if you go to page 479 in column C, to look for the alpha value of 0.05, and you can't find it, but because it's in between two values. So we find the z-score for these two values and divide them by 2, and that's our critical value. That's 645. And step 3 will compute the z-statistic, the obtained value. So the obtained value is 2.5. Here it's a standard deviation for the sampling distribution, so it's a standard error. If you need it, you can go back to previous chapter to find this formula. And we have the z-score of 2.5, and go to page 480 and find the value in the tail is 0.0062. So then this obtained statistic falls into this rejection region. So we need to, our conclusion is to reject the null hypothesis. Effect is the difference between sample mean and the population mean. When sample mean is the same as the population mean, the effect is 0 and insignificant. So we retain the null hypothesis and state that the sample mean is the same as the population mean. But when the sample mean is significantly different from the population mean, the effect is significant. So we reject the null hypothesis. Cohen's d effect size measures the number of standard deviations and effect shifted above or below the population mean. That's why when d is 0, there's no difference between the sample mean and population mean. So we say it's most meaningful to report d with significant effects. And the d increases as the differences between the two means gets larger. And when d is smaller than 0.2, it's considered a small effect. When d is between 0.2 and 0.8, it's a medium effect. And when d is larger than 0.1, it's considered a large effect. In previous slide, the elementary school children's reading proficiency scores, we concluded that the reading program is effective, which means that there is a significant effect and there is a big difference between the sample mean and the population mean. So it is meaningful to report the Cohen's d, and we calculate the d value by, we use the sample mean minus population mean and divided by the standard deviation of the population. And the d value is 0.5. It means that the observed effect 14 shifted half standard deviation above the population mean. In reality, there are two possibilities about the null hypothesis. It's either true or it's false. In our hypothesis testing, there are 4 possible outcomes. We retain the true null hypothesis, or we reject it. We retain the false null hypothesis, or we reject it. And this table is what we usually see in the textbook. If we reject the true null hypothesis, we commit the type 1 error. It's the alpha error. If we retain the false null hypothesis, it's called a type 2 error, and it's a beta error. 1 minus beta is the power. That's the kind of decision we want to make. We'll explain more in the next few slides. Here's the example on page 199 of the two hypothetical populations, class 1 and class 2. The population means are the same, they're both 38. The standard deviations are different. One is 10 and the other one is 2. If we randomly select 30 subjects from each class, and luckily we get the same sample mean, they're both 40. So with the same population mean and the sample mean, we know that the effect should be the same too. It's 40 minus 38, and it's 2. Use this Cohen's d formula, we calculate the effect size. The effect size for class 1 is 0.2. The effect size for class 2 is 1. With the same population mean and the sample mean and a different standard deviation, we get different effect size. As the standard deviation goes up, the effect size goes down. So keep this in your working memory. We'll need it in a little bit. One advantage of knowing effect size d is to use this value to determine the power of detecting an effect. To determine the power, first we need to construct the sampling distribution for both classes. So for class 1, the null hypothesis is the population mean is 38, and the alternative hypothesis is the mean is 40 larger than 38. So this is one-tail directional test. And we set the alpha value at 5%, and it should be in the right tail. In the unit normal table on page 479, you won't be able to find 0.05, but you will see 0.0505 and 0.0495. So 0.05 lays in between those two numbers, and the z-score is the average of 1.64 and 1.65. So 1.645 is the cutoff value. And to use the formula of the cutoff value, we'll also need the standard error of the mean, since this is the sampling distribution. And the standard deviation is 10, and the sample size is 30, so the standard error is 1.82. The cutoff value is 1.645, and we know the population mean, and we know the standard error of the mean, so the sample mean should be 4099, which means 4099 is 1.645 standard deviations above the the population mean. So if we obtain any sample mean larger or equal to 40.99, which is this pink area, and we reject the null hypothesis, even though it's true. So, and that is our alpha error. It's also called a type 1 error. That's to reject the true null hypothesis. And this pink area is also called rejection region. Since the probability under this curve should add up to 1, so the rest of this white area is 1 minus alpha. And if any samples that we selected falls into this area, we accept the true null hypothesis. So that's a smiley face, and that's what we want to see. When the null hypothesis is true, we want to accept it. If we obtain a sample mean equal to or larger than 40.99, we reject the null hypothesis and accept that the alternative hypothesis is true. So to determine the power for this test, we assume that the alternative hypothesis is true and the population mean is 40. So when H1 is true in reality, and we use a Z transformation on this distribution, the Z-score for 40.99 is 0.2946. And that's the power for our test in this example. And power is the likelihood of detecting an effect. If a selected sample mean is equal to or larger than 40.99, it falls into this pink area, and we reject the false null hypothesis and detect the effect between the sample mean and the population mean. So if we retain the false null hypothesis but fail to accept the true alternative hypothesis, and the error is called beta error or type 2 error. Again, the area under this whole curve is 1. So the power is 1 minus beta. So if we reduce type 2 error, we can increase the power. Now we put the previous two slides together and we get this figure 7.10 in our textbook. It shows us when the effect size D is 0.2, this is the power for our test. So keep this one in mind because we'll compare this power to the power for the test in class 2. And imagine if we move this cutoff line to the left, we'll increase both the type 1 error and the power. And if we move it to the left, to the right, we'll reduce both the type 1 error and the power. We want a bigger power, but we don't want a bigger error. For class 2, you can use the same process as we did in class 1, so I won't repeat the details again. To determine the power for class 2, we'll calculate the sample mean corresponding to this cutoff value, and the sample mean is 38.61. So we assume H1 is true and the population mean is 40 and the effect size is 1. So almost this whole pink area is the power for the test. So the point of this comparison is that in class 2, the effect size is larger, so the power is larger.